Week 6, Healthcare Data Mining, Diabetes Prediction with Python. Welcome to Data Mining with a real healthcare dataset. In this session, we will use the Pima Indians diabetes dataset to predict diabetes using binary classification. You will practice loading data, exploring and cleaning it, building models, and checking their accuracy. Data mining helps discover useful patterns from health records. This guides decisions about care, risk, and prevention. Let us dive in and start working with data. Running the cell now. Let us start by turning off warning messages. Warning messages sometimes distract beginners. We are suppressing all warnings to make output easier to read. This line imports the warnings library and disables all warnings. Import numpy as NP. We set the random seed to 42 for reproducibility. Running the cell now. This code sets a fixed random seed and suppresses warnings to create a clean, reproducible environment for our diabetes prediction model. While there is no visible output, this setup ensures that any randomness in data handling or model training will be consistent every time we run the code. This step is crucial for reliable comparisons of model performance throughout our healthcare data mining project. Now let us load the diabetes dataset. We are loading the Pima Indians diabetes dataset, which is a classic health dataset. We import pandas for easy data work. We set the URL of the CSV file hosted online. We define column names to describe each feature like glucose, age, and outcome. We read the CSV file into a data frame with these column names. We print the shape to see the number of rows and columns. We display the first 3 rows to get a quick view of our data. Running the cell now. The output shows the dataset has 768 rows and 9 columns, confirming we have a moderate-sized sample with key health indicators as features. The first 3 rows illustrate patient data including pregnancies, glucose levels, and the binary diabetes outcome, setting the stage for building a predictive classification model. Notice the mix of numeric and categorical variables, which are crucial inputs for our diabetes prediction task. Try changing the URL to see what happens if you load the wrong data. What does the dataset look like? Each row describes one patient. The last column, outcome, is 1 if the patient has diabetes, 0 if not. Let us see how much data we have and how to find useful insights. Running the cell now. Now we will count how many patients were diagnosed with diabetes. This code counts how many records have outcome 0 and how many have outcome 1. This helps us see the balance between the 2 classes. Class balance is important for building fair models. Running the cell now. The output shows the count of patients without diabetes, 0, and with diabetes, 1, in our dataset, with 500 and 268 entries respectively. This helps us understand the class distribution, which is important for modeling and ensures we know how balanced our data is before further analysis. Can you spot if more patients have diabetes or not? Let us now look for missing values in our columns. In medical datasets, 0 can sometimes mean a missing value instead of an actual measurement. This line checks how many zeros are in each column. This helps us plan data cleaning. Running the cell now. This output shows how many zeros appear in each column, which might indicate missing or placeholder values. Notice that key health indicators like insulin and skin thickness have many zeros, suggesting many missing entries to address before analysis. This helps us understand data quality so we can clean it and extract accurate insights about patient diabetes outcomes. Why might 0 be unrealistic for some health data? Let us find out which columns have unrealistic zeros. We pick columns where 0 is very unlikely for a human, like glucose or BMI. We set a list of those column names. We loop through those columns one by one. We count how many times 0 appears in each column. We print the results for each column so we can decide what to fix. Running the cell now. This output shows how many patients have 0 values in key health measurements, which is unusual for these columns and may indicate missing or incorrect data. Noticing that insulin and skin thickness have especially high counts of zeros alerts us to potential data quality issues that we need to address before analysis. This step helps us understand the dataset's integrity and prepares us to clean or impute these values for better insights on diabetes outcomes. Think about what you would do with unrealistic or missing values. Data cleaning, fixing zeros. For our analysis, we will replace zeros in glucose, blood pressure, skin thickness, insulin, and BMI with the column median. Running the cell now. Let us replace unrealistic zeros to improve our data quality. We loop through each selected column where 0 is unrealistic. For each column, we find the median value, ignoring zeros. We change all zeros in that column to the median value. Using median reduces the impact of extreme outliers in our data. We print the first 3 cleaned rows for these columns to verify our changes. Running the cell now. Here we see the first 3 rows of the selected columns after replacing zeros with their respective medians. Notice there are no 0 values anymore, indicating the cleaning step successfully substituted unrealistic zeros with more meaningful median values. This ensures our data is more accurate for analysis by reducing the impact of missing or invalid measurements. Try running this cell twice. Does the output change? Quick exploration, statistics and correlations. Basic statistics and correlation checks help us spot important patterns. For example, does higher glucose mean higher diabetes risk? Running the cell now. Let us see descriptive statistics for all our features. Describe gives us statistics like mean, minimum, and maximum for each column. This helps us understand the range and typical values in our data. Running the cell now. This summary shows key statistics like mean, standard deviation, and ranges for all health features, helping us understand their typical values and spread. Notice, for example, that the average glucose level is around 122 with a wide range up to 199, which may impact diabetes risk outcome. These stats set the stage for exploring correlations to identify which features relate most strongly to diabetes. Find a column with the highest average. What does it measure? Now we will check which features are most linked to diabetes. The correlation matrix helps us find which input features relate most to our target outcome. Higher values mean a stronger relationship. This helps choose features for our model. Running the cell now. This correlation output ranks features by their linear relationship with the diabetes outcome, with values closer to 1 or -1 indicating stronger correlation. Notably, glucose has the highest positive correlation, 0.49, suggesting higher glucose levels are moderately associated with increased diabetes risk, which matches our lesson's goal of identifying key predictors. This quick check guides us on which variables to prioritize in further analysis or modeling. Which feature has the strongest connection to outcome? It is time to visualize the distributions of each feature. Histograms help us see how values are spread for each feature. We import matplotlib for plotting. We use pandas hist method to plot all columns. Tight_layout arranges plots neatly. Show draws the graphs below the cell. Running the cell now. This output shows histograms for each feature in the dataset, providing a clear view of their distributions and shapes. Notice how some variables may be skewed or have distinct ranges, which can influence further analysis like correlation tests. This quick visualization helps us understand the data's characteristics before checking relationships, such as how glucose levels relate to diabetes risk. Look for features with unusual shapes or spikes in the plots. Now we will separate inputs and target for modeling. This section creates the input features, x, and the target variable, y, for the model. X is assigned all columns from the data frame except the outcome column, which will be used as input features. Y is assigned the outcome column from the data frame, which is the target variable we want to predict. Running the cell now. Here, we've split the dataset into inputs x and the target variable y, which is outcome indicating diabetes presence. This setup is essential for analyzing how each feature, like glucose levels, relates to the target. Having separated these, we can now easily explore statistics and correlations to uncover meaningful patterns in the data. We will split the data to test the model fairly. Splitting keeps some data hidden from the model until the very end. Train_test_split divides inputs and targets into training and test parts. We use 80% for training and 20% for testing. Random_state sets the seed for reproducibility. We print the shapes to confirm correct splitting. Running the cell now. Here, the output shows the shapes of the training and test datasets after splitting, with 614 samples in training and 154 in testing, each having 8 features. This step is crucial for creating reliable models by training on one subset and validating on another, ensuring our latest statistical and correlation analyses are based on properly partitioned data. Try changing test_size to 0.3 for a different split. Model time, logistic regression. Logistic regression helps predict binary outcomes, in this case, diabetes yes or no. Running the cell now. Let us train a simple model to predict diabetes. This line is a comment explaining that we will fit a logistic regression model. We import the logistic regression class from the scikit-learn library to use it for modeling. We create an instance of logistic regression, setting max_iter to 200 to allow more iterations for convergence. We train the logistic regression model using the training data features and labels. Running the cell now. This output confirms that the logistic regression model was successfully initialized with a maximum of 200 iterations to ensure convergence. It's an important step before training the model to predict diabetes presence, yes/no, based on the features in x_train. This sets up the foundation for making binary predictions in the next steps. Try using max_iter equals 1000 if the model does not converge. Now let us see how well our model did. We use the trained model to predict the chance of diabetes on the test data. We generate predictions from the classifier for the test feature set. We import accuracy scoring, which compares predictions to the real answers. We calculate accuracy, the percent of times our model is correct. We print the accuracy value as a percent. Running the cell now. The output shows an accuracy of 0.75, meaning the logistic regression model correctly predicted diabetes status 75% of the time on unseen test data. This highlights the model's effectiveness in distinguishing between diabetic and non-diabetic cases, reinforcing how logistic regression can be used for reliable binary classification. What percentage accuracy did your model get? High enough for health decisions? Let us look deeper at our model's correct and incorrect guesses. This line is a comment explaining that we will show a confusion matrix for more detail. Here we import the confusion_matrix function from scikit-learn's metrics module. We compute the confusion matrix by comparing the true labels y_test with the predicted labels y_pred. We print the resulting confusion matrix to see the detailed counts. Running the cell now. This confusion matrix shows how well our logistic regression model predicts diabetes outcomes. 82 true negatives and 34 true positives on the diagonal indicate correct predictions, while 17 false positives and 21 false negatives are off-diagonal errors. Notice the balance between correctly and incorrectly classified cases, which helps us evaluate the model's accuracy beyond simple metrics. This detailed breakdown is key to understanding where the model succeeds and where it may need improvement. Can you explain what each cell in the matrix means? Let us use our model to predict diabetes for a brand new person. This comment explains that we are trying to predict diabetes for one new patient input. We import the NumPy library to work with arrays. We create a NumPy array representing the new patient's medical data. We use the trained classifier to predict diabetes for this new patient data. We print a clear message saying whether the patient is likely to develop diabetes based on the prediction. Running the cell now. This output shows the model's prediction for a single new patient, indicating they are unlikely to develop diabetes. Notice how the logistic regression model uses the input features to classify the patient into a binary outcome, yes or no. This step demonstrates how our trained model can provide practical, individual risk assessments. Practice: ask a friend to invent their own test results and see what the model predicts. If you found this lesson useful, please like the video and subscribe for more data science content. Congratulations! You have cleaned, explored, and built a predictive diabetes model in Python. Try changing parameters or models to see what improves results. Data mining can help spot health risks, guide care, and save lives. Ready for more? Try another health dataset or add more features. Keep practicing, and share your progress by commenting below. Running the cell now. Challenge: what happens to your accuracy if you drop or combine some features? Tell us in the comments, and hit subscribe to stay up to date with these lessons.